Okay guys, today we're going to be talking about bond enthalpies and how you can use bond enthalpies to calculate the enthalpy of a reaction. And I kid you not, this is like my 5th time, so if I have any more mistakes, I'm just going to deal with them in the video. Sorry guys, my brain is just absolutely fried. Okay, so what are bond enthalpies? Bond enthalpies are the average energy changes associated with the making and breaking of chemical bonds. Breaking bonds is endothermic, as energy is required in order to break the attractive forces between the atoms, whereas making bonds is exothermic, as when 2 or more atoms bind together, their bonded state is more stable than that of their unbonded state, so energy is released at the time of bonding. So the key thing here is that bonding enthalpies are the average energy changes. They're averages. We take an average of all carbon-hydrogen bonds and use that as an average energy. But carbon-hydrogen bonds in different molecules can actually have different energies. So these are not the most accurate because they are an average, but they get you in the ballpark. And then breaking bonds is endothermic, making bonds is exothermic. And so we're going to talk now about factors affecting the strength of bonds, and I just want you to kind of just listen to this. Don't freak out about it because it's a little complicated, but just listen. So as the number of shared electrons in a bond increases, the attraction between the electrons and the protons of the bonded nuclei increases as well, so the bond increases. This means that triple bonds are stronger than double bonds, which are stronger than single bonds. And you're actually going to see this in the bond enthalpies. When you look at a carbon-carbon triple bond, it has a higher enthalpy than a carbon-carbon double bond, which has a higher enthalpy than a carbon-carbon single bond. When the radius of the bonded atoms decreases, the protons and electrons of the bond are closer to each other, so the attraction increases on one end, making the bond weaker. It was very confusing, so let's look at it. So if you have a smaller radius here, this smaller distance makes a larger attraction, this larger distance makes a smaller attraction. It becomes kind of uneven, and it's something to do specifically with the actual distance, because it doesn't have to just be an uneven pull. It's the fact that you've got these really uneven distances, and it makes the attraction weaker. And then when the number of protons increases, or the effective nuclear charge of a nucleus increases, the attraction between the protons and electrons increases, increasing bond strength. So let's look at that. And so here we have equal distances but stronger poles, and so the larger charge has a larger attraction, the smaller charge has a smaller attraction, and it just increases the bond strength because there's a larger attraction between the positive and the negative. Okay, don't worry too much about it. Mostly just take away that the more electrons in a bond, the stronger the bond. So double is stronger than single, but double is weaker than triple. All right, let's look at endo and exothermic reactions and energy. So during every chemical reaction, sufficient energy must first be present to break the bonds before you can make bonds, and this is called the activation energy. And the activation energy is defined as the minimum energy required by the reactants in order to form the products. And so before you can go from reactant to product, you have to go over this hump, this activation energy. You have to have this amount of energy inherent in you or in your surroundings in order to break the bonds here before you can make the bonds here. And then the change in energy from reactants to products is your delta H, which is your enthalpy change. So some reactions have small activation energies because there is enough energy in the surroundings to get them started, whereas others have higher activation energies and need to absorb much more heat in order to break the bonds. Okay? Just some basic ideas to take there. And let's see how this affects bond enthalpies. Since chemical reactions are just the breaking and forming of bonds, you can calculate the enthalpy change of a reaction by looking at the bond enthalpies of the reactants and the products. And here, the enthalpy change of a reaction is equal to the sum of the enthalpy of the bonds broken in the reactants minus the sum of the enthalpies formed in the products. And so this is the first time where it's actually reactants minus products instead of products minus reactants. And it's because it takes energy to break the bonds. And the unit for enthalpy in this situation is kilojoules, as the enthalpies of bonds are in kilojoules per mole, and you multiply the enthalpies by the number of moles of each bond type. Now we're going to do an example, and there's going to be a lot of words, and I want you to not stress too much about it. Just take it step by step. So if I have carbon monoxide and I mix it with water, I make carbon dioxide and hydrogen gas. And what is the enthalpy of this reaction? And so using the bond enthalpy table that you've been given, determine what the enthalpy of the above reaction is, given the bond in carbon monoxide has a bond enthalpy of 1,077 kilojoules per mole. So you've been given that it's 1,077 kilojoules per mole already. And if you look, it's 1 carbon, 1 oxygen, 1 carbon monoxide bond. So I have 1 mole times 1,077 kilojoules. If I look at water, I have 2 hydrogens bonded to 1 oxygen. So I have 2 hydrogen-oxygen bonds, which in your table, you'll see that that has a hydrogen-oxygen bond has an enthalpy of 465 kilojoules per mole. But I have 2 of them, so I have 2 moles worth. Carbon dioxide has 2 moles worth of carbon-oxygen double bonds, which has an enthalpy of 532 kilojoules per mole. And then in hydrogen gas, I just have 1 hydrogen bound to 1 hydrogen, so 1 mole of an HH bond with 435 kilojoules per mole. So my change in enthalpy is going to be my reactants minus my products, so bonds broken minus bonds formed. So 1 mole times 1,077 kilojoules plus 2 moles times 465 kilojoules per mole minus 2 times 532 plus 1 times 435 gives you 2,007 kilojoules minus 1,499 kilojoules, so an enthalpy change of 508 kilojoules. So this would be an endothermic reaction, meaning it takes energy in order to do it. Okay? Now another way to look at this is to think about it more in terms of structure, because maybe you can't just physically see or visually see what's going on and you need to draw out the structures. And so if I'm looking at this, I see that for my bonds broken, I need to break 1, 2, 3, 4, 5, 6 carbon-hydrogen bonds. So I have 6 moles of carbon-hydrogen bonds. I have to break 1 carbon-carbon bond and 1 chlorine-chlorine bond. And then I'm going to make 1, 2, 3, 4, 5 carbon-hydrogen bonds, 1 carbon-carbon bond, and 1 carbon-chlorine bond, and 1 hydrogen-chlorine bond. When you plug in all the data from the enthalpy table, you get that. I'm not going to read it out to you. And when you do the math, you get 3,095 kilojoules minus 3,200 kilojoules, which is an enthalpy change of negative 105 kilojoules. So this is an exothermic reaction. Now, there's a way to actually simplify this, and I don't know if you guys, some of you might just see this right off the bat, but there's only 2 bonds that are actually being broken right here. This carbon-hydrogen bond is broken, and this chlorine-chlorine bond is broken. And then we only make 2 bonds. We make a carbon-chlorine bond and a hydrogen-chlorine bond. Sorry, I didn't mean to go right over that hydrogen. Ooh, look at that. Oh, there we go. So these are the only bonds that are actually made and broken. And so I can leave out these 5 carbon-hydrogen bonds because they stay the same, and this carbon-carbon bond. And I can leave that out and kind of simplify it if I just do the following. Oops. So if I look at this, again, I'm only breaking 1 carbon-hydrogen bond and 1 chlorine-chlorine bond, and then I'm only making 1 chlorine-carbon bond and 1 hydrogen-chlorine bond. And so if I plug that in, it becomes 657 kilojoules minus 762 kilojoules. You still get the same answer of minus 105 kilojoules. It's just a lot less math. So if you can see which bonds are being broken and which ones are being formed and you want to use the shortcut, great. If not, you can do the long way, and that's just fine. Either one works. So tomorrow in class, we're going to be practicing calculating the enthalpy of reaction from bond enthalpies, and we're going to have a lot of fun. All right, thanks guys. Have a good night.